Hello everyone, welcome to another Quad Education Test Prep Fundamentals video. My name is Tom and today I'm doing a follow-on on my unit circle video. So in that video I said that unit circles as a topic is overtaught and overcomplicated, and I feel that the same thing is true of this topic, which is trigonometric waves and functions. So it sounds complicated but really not too bad, and hopefully I can prove that once again in this video, so let's take a look. Okay, we're talking about trigonometric waves. That sounds pretty fancy, but I think we'll find that, like many things, it's pretty sensible when you know really what you're looking at. So before we can do that, let's go ahead and do a quick little review. First of all, we're talking about trigonometry, so remember SOHCAHTOA. So meaning the sine of an angle is equal to the opposite over the hypotenuse, cosine of an angle is the adjacent over the hypotenuse, and the tangent is just the opposite over the adjacent. I will say that I've seen a tan wave like once in ever, and other than it being really interesting to look at, it's probably not really worth talking about, so I am not going to talk about it. The other thing, and just sort of in the interest of keeping this video in under 20 minutes, sine waves and cosine waves are very close to the same thing, because we'll see here they're just dealing with the same triangle. It's just one deals with the adjacent. Like I mentioned, the adjacent is the x dimension, and one deals with the y, which is the opposite. And it's part of, you could essentially do for any triangle, it's the same triangle, just with different sides to it. So then just a little bit more review here, like what we spoke about last time, which was the fact that all the unit circle is we're drawing a line to the circumference, which is just the radius. And then we are measuring what happens as far as, what happens to the opposite here, what happens to the adjacent here. Now, what I'll demonstrate here is what happens as the radius moves from here at 0 degrees up to here at 90 degrees. So down here, we would start like right there, and basically we just draw our little right angle, and we can see a pretty small opposite there. And if we're doing sine, opposite is the sign that we're worried about, right? Because the hypotenuse is fixed, it does not change. We can see now that that's much longer. And even longer if we go here, that's pretty long. All the way till we go way up here, where you can see that the opposite here is very nearly just as long as the hypotenuse itself. And indeed, when we get to the 90-degree angle itself, you can see that, or maybe you kind of can't see, but you can imagine that the hypotenuse and the opposite are actually the same length, which is our first big little point here, which is why the sine of 90 degrees, or pi over 2 if you like, is going to be equal to 1. Because basically here, going straight up, that opposite is now the length of the radius, and anything over itself is just 1. And then what happens is after that, past the 90-degree mark, we can see that our hypotenuse, or excuse me, we can see that our opposite is starting to shrink until we go all the way down here to 180, where indeed it is 0 again, because it's not going up or down from the x-axis at all. It is 0. There is no opposite. And then the really interesting thing again is we pass 180 degrees, and you can see that our opposite is actually negative, because it is below the x-intercept, the x-axis. So this tells us why, as we go further and further toward 270 degrees, that our opposite is getting more and more negative until we get down here at 270 degrees, where we can see that it is now, instead of being r, it is negative r, which is why the sine of 270 degrees, or 3 pi over 2 if you're doing radians, that's going to be negative r over r, which is negative 1. And then past that, we're back to our declining, our shrinking opposite until we get back to the beginning here, where once again, the sine of 0 or 360 degrees is going to be 0. And and like I mentioned, cosine and sine are pretty much the same thing, just sort of, they're literally complements of one another. They share 90 degrees between them. And if we look at this behavior of increasing this angle of the radius over time, we can see here that the adjacent is doing exactly the opposite. So here at 0 degrees, the adjacent is exactly as long as the radius, and now you can see it's getting shorter and shorter and shorter until it's 0 at 90 degrees. And then past that, it's getting longer and longer and longer, except it's negative till we get to 180 degrees, where the cosine of 180 degrees, or pi, is going to be -1. And then we can see that it starts to shrink and shrink, going back to here, it being 0 at 270. And then it starts to grow again and grows back to 1 here at 360. And hopefully this is visualized for you the pattern that sine and cosine are taking as we spin around the axis like this. And the reason that I'm hoping that you do that is because we're going to look at it on its own graph now. So if we think about the sine, right? If we took the sine of y was just equal to the sine of x, and we started at our 0, and I'll just put a little sample unit circle up here where see a very bad circle, and we start right there, and there is no opposite. We go up, as we go from 0 to 90 degrees, we're approaching the value of 1. And then when we get to 180 degrees, you can see that we're back down to 0. And then we get to 270 degrees, where we have reached -1, and then back to 360 degrees, where we are back at 0. And it looks something like this. It's this nice, maybe I'll try one more time. It looks something like this. This nice, smooth, overshot it a little bit there, but just not an artist, I'm a tutor. And this nice, smooth sine wave here. And what this will do is it'll just continue forever, this nice, smooth wave. And if we were to look at what that would be for the cosine wave, it's the same thing, just moved back by pi over 2, or 90 degrees. Same behavior, it's just shifted to the left a little bit. And thinking about this makes sense because it's a circle. It should repeat endlessly, and it should be nice and smooth like this. And so what these tests will ask you is how we shift these. And the nice thing is shifting a trig wave is exactly the same as shifting any other function. And so that general function looks like this. We have a sine b x minus c plus d, and you really won't see a whole lot of this on these tests. It's mostly going to be this one, or this one. So a, b, and d is what you're usually going to see when they do function shifts for a sine wave. And basically all that's happening is we have our regular sine wave, looks like this. We would say a is going to affect the amplitude. That's how tall it is. So that's going to say this maximum will be higher and this minimum would be lower. So we'd go higher with the same intercept point, and then lower will be a different amplitude. The period of the wave, what that's going to mean is it's going to spin faster. So that would mean that instead of taking this amount of time, it might take half the time to get there. So instead of taking all the way like this, maybe something like that, where it's spinning twice as fast. And then we have our left-right shift, which starts to break down as far as sense goes, if you ask me, since this is so symmetrical and periodized. If you were to move it over by 2 pi, it would look exactly the same. And if you were to move a sine wave over, 90 degrees, then it would just be sine effectively. So they kind of don't do a lot with this, but then they do quite a bit with d, which is moving it up and down. So we have our sine wave look like this. An upshift may just be the same thing, but just moved up a little bit. And that makes sense. It's just like a parabola or a linear equation. You can make it taller, shorter. You could also flip it upside down if you made this negative. This increases the speed right here. This is a left-right shift, and this is an up-down shift. Pretty straightforward. And at the end of the day, they're really only going to ask you about trig waves in the ACT, and you could probably graph this by brute force if you really wanted to. Okay, that seems like an above average amount of talking for one day. Here's our practice problems. Go ahead and try the first one and see how you do. Okay, let's take a look. So we have 4.5 for our amplitude for this wave, which is to say that let's just say that it's a cosine wave. That means that it looks like this. That means that the top here is 4.5, the bottom here is negative 4.5. So basically what happens is we need to either move this up so high that the bottom of this wave does not touch, or so low that the top of the wave no longer touches, so like that. And all that is to say we need to either just move this up 4.5, more than 4.5, or down more than 4.5. That's effectively what this one says, where we say, okay, it's either we have less than 4.5 is how much d is, or more than 4.5. And that's a pretty straightforward one to visualize. Let's take a look at the next one. Okay, here's our next practice problem. See how this one goes. Okay, let's take a look. So this is one that I found in a very recently released ACT, and I really like this question because it's pretty difficult. So they're saying for all radian measures of x greater than 0, which of the following expressions is equal to cosine of x? And like we've said, cosine of x looks like this, where it repeats starting at 1 and repeats every 360 degrees, or in this case, 2 pi radians. And so if we were to move it forward pi over 2, basically that would look like this, which is not the same thing at all. So I'm going to say no to that. And then the same thing is kind of true for 180 degrees. So in that case, instead of starting there, we would start right there, which would be, we start down here and go like this. And sometimes that's the same when it intercepts, but everywhere else it's just the opposite sign, which doesn't make sense. And then here we're 3 pi over 2, so that would be starting from, let's take a look. So right there we have cosine of 0, and that's going to mean that we're sort of starting like right there. So that really won't work either. But what I really like here is the idea that 2 pi is right there. And 2 pi is the same thing as 0. So what that's really saying is that the cosine of x is equal to the negative cosine of x. And that's really well illustrated if I clear this out a little bit and we look at what cosine of x looks like. It's like this. And what you'll notice is that's actually a vertical line of symmetry for a cosine wave, which is to say the right is always exactly the same as to the left. And that is why E is correct, which I really like. I think that's really interesting. Okay, that's it for this video. Remember, trigonometric waves are just a visual description of the intuitive process that occurs when we rotate a radius around the unit circle. If you're ever not quite sure where you may be in that wave, maybe it's best just to make a quick sketch and see what it looks like. If you found this material useful, we hope that you will like and share the video and subscribe to Quad Education. If you require any kind of tutoring, please reach out to us. Thank you for watching, and I hope you have a great day.